Hello and welcome. Today, we're diving into a fascinating field often misunderstood: chaos theory. Most people hear chaos and think randomness, pure unpredictability. But that's not quite right. Chaos theory is actually about finding the hidden order within seemingly chaotic, complex systems. These systems are deterministic, meaning they follow underlying rules. So where does the unpredictability come from? It stems from something called extreme sensitivity to initial conditions. You've probably heard of the most famous example, the butterfly effect. The idea is that a butterfly flapping its wings in Brazil could theoretically set off a tornado in Texas weeks later. A tiny, almost imperceptible change at the start can lead to massively different outcomes down the line. This makes long-term prediction incredibly difficult, sometimes impossible. But crucially, this isn't pure randomness. It's a result of nonlinear dynamics and feedback loops within the system itself. Understanding these dynamics is the core of chaos theory. Think about weather forecasting. Meteorologist Edward Lorenz stumbled upon this when he found that minuscule changes in his weather model's input data created wildly different forecasts. This showed the inherent limits of predicting weather far into the future. However, chaos theory isn't useless here. It helps meteorologists understand atmospheric behavior, quantify uncertainty, and improve short-term predictions using techniques like ensemble forecasting, where they run multiple simulations with slightly varied starting points. Nature is full of chaotic dynamics. In ecology, it helps model the sometimes wild fluctuations we see in animal populations, or the intricate web of interactions in an ecosystem. Those sudden booms and crashes aren't always random. They can follow underlying chaotic patterns. Even within our own bodies, chaos theory applies. It helps analyze complex rhythms like heartbeats and brain activity. Things like heart arrhythmias or specific brainwave patterns can sometimes be understood through the lens of chaos, potentially helping diagnose issues. We also see related concepts like fractals, those intricate self-similar shapes found everywhere from coastlines and snowflakes to the branching of trees, rivers, and even our blood vessels. But chaos theory isn't just about observing nature. We're actively using its principles in technology and society. Engineers use it to understand complex phenomena like fluid turbulence or vibrations in structures, helping them design more resilient buildings or optimize processes. In finance, while predicting the stock market precisely remains a holy grail, chaos theory offers tools to understand market volatility and assess risk. Markets show that sensitivity, a single large trade can shift direction, and feedback loops where rising prices encourage more buying. Even secure communications benefit. The unpredictable nature of chaotic signals is perfect for creating encryption methods that are extremely hard to crack without the right key. And in computer science and AI, chaos theory helps analyze complex networks, like social media or the internet, understanding how small issues could cascade. There is also exciting work integrating chaos with AI, using machine learning to model and find patterns in chaotic data, pushing the boundaries of prediction. So while chaos theory highlights the limits of looking far ahead in complex systems, it gives us powerful ways to understand their structure and behavior now. It reveals hidden patterns, attractors, and the fractal nature within apparent disorder. By embracing this complexity, we can improve short-term forecasts, manage risks better, and drive innovation. Research continues to merge chaos theory with big data and AI, explore quantum chaos, and apply these ideas to everything from power grids to brain pathways. It teaches us that unpredictability doesn't mean incomprehensibility. There is order and understanding to be found, even in chaos. Thanks for tuning in.